equal to c squared minus by 4mk divided by 2m. The problem comes with this now. Okay, over here, this value over here that I'm going to highlight in yellow, right? This value will be what? Negative. You cannot square root a negative number because it does not make sense in the real world. So in order to make it positive, we let omega is equal to 4mk minus c squared divided by 2m. Okay. And then there's another term that we have to know is that omega n is equal to square root k over m. Sylvie, my folder still with you? Yes? I'm kind of desperate now, but anyway. So now you have this expression. Okay, you have this expression. So the reason why we do the flip so that this can become a what? Positive number. Okay. So now we are going to adjust this formula. Okay, so to adjust this formula, what we are going to do is we are going to have 4mk over 4m squared minus by c squared over 4m squared. I'm going to bring the square root to the denominator. Okay, so what we are going to do now is I'm going to cancel this, I'm going to cancel this, I'm going to cancel this, I'm going to cancel this. So what we have now is equal to square root of k over m minus by c squared over 4m squared. We want to introduce omega n into this expression. Okay, we want to introduce omega n to this expression. So over here, we have square root k over m multiplied by the square root 1 minus by c squared over 4mk. So from here, we are going to let zeta is equal to square root of c squared over 4mk. So from here, the expression will become omega n square root of 1 minus by zeta squared. Okay. So we know what is our omega equal to. And then for alpha, we also know that it's c over 2m. And this is also equal to zeta multiplied by omega n. Yes. Say it again. What do you mean? Why is it square root? Okay. So with this, zeta is equal to square root c squared over 4mk multiplied by square root k over m. close bracket. So when you deal with this now, oh, sorry. This will be equal to what? This will be equal to square root c squared over 4m squared. This will be equal to c over 2m. So from here, we know that we can change the expression, right? We can change the, so therefore, the general equation or the general solution will be x as a function of time is equal to e minus zeta omega nt bracket c1 cos omega t plus by c2 sine omega t. Now the omega over here is also equal to omega d. Okay, so it's damped natural frequency. Yes. Distracting me because of the performance measure. If not, you have to key in so many numbers in one equation, you can get confused. Okay, and there are other purposes when you learn control later, control theory, why they need to have zeta. Now, if you check on your notes, am I okay so far or I make mistake? Now, we have gone through how many pages? One page. Okay, I cannot even remember your name at all. I only remember Sylvie. I met her today. The rest, I do apologize. I'll make an effort. Okay, some of you, I taught you twice before. I know Bill. Okay, the rest, I'm sorry. Okay, but I'll try to make an effort. Right. So from here, yes. Oh, I do apologize. The next part, I know if you read my professor, he said Eugene swears a lot. Indeed, he does. Why? Because at this time, it's holy shit time. Why? Because now I'm going to derive performance measure. Okay, then after performance measure, I'm going to derive undamped natural frequency in force vibration. You guys are Eugene, good luck. Okay. Right, so from here, we know we are going to look at a performance measure. So how I remember performance measure is I just need to remember the graph. Remember I told you how important that graph is? Yes or no? Right? So I'm going to sketch out. Just remember the graph. It's so much easier remembering graph than remember a phone number. Yes or no? Okay. So we remember this. While writing all this, I know it's boring. I got a call from call center that say, Eugene, you have purchased a computer from Amazon. I call back that number and I said, how do you know that I purchased the computer? You are right. And then the caller says, there's something wrong with the purchase. I said, there's nothing wrong. I use cash. He got so pissed off that he put down the phone. Okay, so whenever you have a call like this, just say you use cash. They cannot get any money from you. Okay. Right. This is our X steady state. And the first thing we have to remember over here, this is pi. And over here, this is pi over 2. And over here, this is 3 pi. The distance from here to here is known as our overshoot. And a certain condition we know that this limits over here from the red line is x, it's no good to call x. is all of a sudden my alphabet is not very good. H percentage of HSS, where H is an arbitrary number. Whatever you want. So with this, we know that this is our rise time. Over here, this is our peak time. And then when it fall in range over here, whatever the number is, I don't know. This is the settling time. Okay. So from here, the general expression, okay, is x as a function of time. This will be equal to E minus zeta omega nt bracket C1 cos omega t plus by C2 sine omega t, and this is plus xxx. So you just need to remember rise time, which is equal to TR, right? So you know that omega TR is equal to pi over 2. TR is equal to pi divided by 2 omega. And omega over here is your damped natural frequency. Then you have your peak time. And this is your TP. And TP is omega TP is equal to what? Pi. TP is equal to pi over omega. Okay. So we have done our rise time. We have done our peak time. Now is to do our what? Overshoot. Yeah. So to do our overshoot, or before we do our overshoot, there's only one point that we are very sure of. I repeat again, there's only one point that we're very sure of, is this point over here where x, where time or omega t is equal to 0, x is equal to 0. So this defines our boundary condition. Okay, this defines our boundary condition. So remember, this graph is so useful. Yes. Omega t on the x-axis, because it's dependent on the excitation frequency, omega. Okay, so you cannot just put time, it's too generalized again. Okay, so we put omega t is all dependent on omega. Okay, so on the x-axis, in all the graph you look on performance measure, x-axis is always omega t, y-axis is the amplitude of vibration. So from here, I don't know what to do now. Boundary condition. So x as a function of time is equal to E minus zeta omega nt bracket C1 cos omega t plus by C2 sine omega t plus by xxx. We're going to substitute omega t is equal to 0, x is also equal to 0. So from here, we know that this is 0, this is equal to 1. So you have C1 cos omega 0 is equal to 1 plus by 0 plus by xxs. So we now know that C1 is equal to minus xss. Okay. So from here, we know that x as a function of time is equal to E minus zeta omega nt bracket C1 cos omega t or minus xxs cos omega t plus by C2 sine omega t. and then plus by XSS. Right. So now what we want to determine now is overshoot. I repeat again, what we want to determine now is the overshoot. So I will copy this equation. Okay. So again, by remembering the graph, overshoot, or we're going to determine the function of overshoot. So we know that overshoot occurs when omega t is equal to what? Pi. Yes or no? Right? From where? Anyone? From here. You see this?